This is a video about non-conservative work and going through an example of that. Now I can try and do this in small pieces, but I think I'd like to do this as a little bit longer of a problem that approaches non-conservative work maybe a couple different ways, all at once. So we'll do this. I'm going to have a hill. And then it's going to go flat, and then maybe we'll have another incline over here. We'll push on a box, and we'll give this box a mass of 50 kilograms. We are going to push on it with a force of 200 newtons. And we're going to do that over a distance of, let's call that 4 meters. I guess the person's really tall. This box is then going to slide down a hill, and we'll give the hill a height of 10 meters. And while it's on this part of the hill, we're going to give it no friction. We are going to, I suppose, put some pretty serious spikes on our shoes so that we can walk in this no friction space, but that's okay. Once we get to the bottom here, we are going to add in friction, just for a stretch. And we'll make that a stretch of, I don't want to use 10 meters because I've already used that and I'd like the numbers to be unique. So we'll go 8 meters, make it a little bit shorter. And for that stretch, we're going to give this thing a coefficient of kinetic friction of 0.2. It's not a lot of friction, but it's some. And then we get back to a space with no friction. And what I would like to know in the end is how high up the hill do we go? I will tell you with absolute full disclosure that I didn't work out the numbers ahead of time. It's possible that this friction is enough to bring this thing to a stop and that we don't go up the hill at all. I am in this adventure as much as you are. So let's get started. I'm going to break this seemingly big problem, it is a big problem, into a bunch of smaller problems. So I'm going to start with point A is before I bring this across that distance. Point B is after I've pushed it. Point C is going to be right here before the friction hits. Point D will be right after the friction is over. And point E is when I come to rest at some highest point. How high up the hill will the box reach? So what I have going on first is that from A to B, I am adding energy into the system with the push. From B to C, so let's see, with that push, I am saying non-conservative work. From B to C, I'm moving down a hill, and everything is conserved. I've got no friction for moving energy from the system. I've got nothing else I'm adding. From C to D, I'm on this friction path. So I have non-conservative work. And then from D to E, I am climbing a hill again. So my energy is conserved. Yes, from D to here, I'm not really climbing a hill, but I've got no friction, so it doesn't actually matter. It's not gonna make any kind of a difference. So there's kind of my roadmap of the whole problem. I'm going to do this. I'm going to start with my energy, business, potential energy, kinetic energy. I will leave a space in between, and then I will have a spot for work, non-conservative work. So let's look at point A, point B, point C, point D, whole big table. But at this point, we like tables, or at least see that they're useful. It could be that when you are done with this course, that you are done with tables. It's a good way of organizing our thoughts, though. Here we go. At point A, we have some amount of potential energy. We have some amount of kinetic energy, maybe. At point A, I'm going to say that I have a potential energy of 0. So for points A to B, I would like to set that to be the ground for 0. No potential energy, no potential energy. Or I do have potential energy, but it's not changing. Kinetic energy. I start with no kinetic energy, and I'm going to end up with a half m VB squared. And in between there, I have done some amount of non-conservative work, and I'm going to have to figure that out. So in between, I have a box, and as far as forces go, I have mg pointing downward, I have a normal force pointing upward, and I have a push force going to the right. I can set up my axis y, x, and have a free body diagram. These two are going to cancel each other because I'm just working horizontally anyway, so all I have, my only force really acting, is my push force, and it's to the right. My non-conservative work is going to be my push force multiplied by the distance that I travel. Now my push force, I said, was, 200 newtons, and I'm going to do that for 4 meters. So this, as a reminder, is 200 newtons. This, as a reminder, is 4 meters. And that is what's going on in between points A and B. Next up, at point C, now I'm going to have to really do something. So maybe I'm going to change these just a little bit. I'm actually not. I'm going to make a point of this. I started 10 meters up, and I started by saying this right here is my height equals 0. Well, I'm kind of committed to that now because I'm not going to go back and erase it. Guess I could, but I'm not going to right now. What that means, though, is that down here, my height is going to be negative 10 meters. I'm 10 meters below where I started. Not a big deal. I can put in a negative number. They are not that scary. So at point C, I've got an mgHc, with hc being negative 10 meters. I've got a kinetic energy, half m vc squared. And being that the work is kind of about the transition from one to the other, so this was the work from A to B, and that was positive, I was adding. The work done between B and C is going to be 0, my non-conservative work, because from B to C, I am in a conservation of energy situation. So that's nice. And there's the work, the non-conservative work from C. Now from C to D. At point D, my energy, my potential energy is mg hd, and that's still negative 10 meters. My kinetic energy, half times mass times my speed at d squared. And the work that I've done in going from C to D, I do have a non-conservative work situation, so I have to figure out the work that I've done. If I draw my free body diagram, I get a normal force, I get an mg, I've got nothing pushing to the right even though I'm moving to the right, and I've got friction. My normal force and my mg are going to cancel. I can again set up my axis x, y, and I've got a free body diagram. Let's try that again. I've got a free body diagram. Now the work that I'm doing, I do need my y component things here because my frictional force is equal to mu kinetic times my normal force. My normal force is equal to gravity because they're going to balance. So I needed my y direction stuff just to be able to find what that friction was. The work that I'm doing is going to be equal to my frictional force, which is mu k mg, that's the force part, times the distance. So this one back here was the distance from A to B. This one is going to be the distance from C to D. And that friction is taking energy out of my system. I'm moving to the right, my force points to the left, so I get a minus sign. And there is the work that I'm doing between C and D. Last part. At E. So the work done between D and E, that's going to be 0 again, because it's a conservative portion. The potential energy at E is not going to be 0. I'm going somewhere up my hill. mg, height at E. My kinetic energy, if I'm finding how far I reach, that's going to be 0. So now I have my whole table for all the different parts and for the work done in each region. Deep breath, gonna start moving. I'm looking for how high up the hill I'm going to reach. So I'm looking for this final height, E. I can run this problem a handful of different ways. I can say my energy at A plus the work done is equal to my energy at B and find the speed at B. Let me do that. Bear with me because this problem is going to be a little bit on the long end, and then I'm going to show you a short way of doing it too. So my energy at A plus my non-conservative work from A to B is equal to my energy at B. Energy at A is 0 plus push force times the distance from A to B is equal to half m VB squared. Solving for VB, I'm going to get 2 times my push force times my distance from A to B, all over mass, all under a square root, and I can plug those numbers in. I had a push force of 200 newtons. I had a distance of 4 meters. I'm grabbing those from here because I wrote them down to make sure that they would be easy to find. Over the mass that I should have written down, mass was 50 kilograms. So over 50 kilograms. And I'm going to take a square root of that whole thing. 2 times 200 is 400, times 4 is 1600, over 50 is 32, and then the square root of 32 is 5.7. So I'm going to get 5.7 meters per second is my speed at B. Now I told you I'm going to give you a faster way of doing this problem later. For right now, I'm going to work through it this way because a lot of times when you get these problems, they ask you for all these intermediate steps anyway, so we might as well get the intermediate steps out of the way. There's my A to B part. Next up, B to C. My energy at B is equal to my energy at C because I have no non-conservative work in the process. So, half m VB squared equals mghc plus half m VC squared. This time my mass cancels. I'm solving for VC. So my VC is going to be half VB squared minus GHC. I'm going to multiply that whole thing by 2, and I'm going to take a square root. So I get half of my 5.7 meters per second squared minus G times HC. Again, HC was negative 10 meters. This means I'm adding a term, right? Negative and negative cancel. So I'm adding a term, and that makes sense because at C, which is at the bottom of a hill, I should be moving faster than I was at the top of the hill. And I said I was going to take this whole thing and multiply by 2. So that's what's under the square root. 32 times a half is 16 plus 100 is 116 times 2 is 232, and the square root of 232 is 15.2 meters per second. That is my speed at C, and that is fast enough to where I am pretty confident we are going to make it through that frictioned region. And that's good. So that is my B to C problem. Now C to D. My energy at C would be equal to my energy at D, but I've got this non-conservative work, so plus non-conservative work equals energy at D. Energy at D. Energy at C, mghc plus half mvc squared, and then plus my non-conservative work, so minus mu k mg d equals my energy at D. Speed at D squared. Alright, I have mass in every term, so I can cancel those out. I also have this term right here, which is the same as this term right here. So I'm going to cancel out those whole terms. I'm solving for the speed at D. So my speed at D is going to be equal to, I've got a half VC squared minus mu k GD. I'm going to multiply that whole thing by 2 and take a square root. So I get that my speed at D is 2 times a half speed at VC minus my coefficient of friction times gravity times the distance, and I'm going to take a square root. And when I do that, I get that my speed at D works out to be 14.1 meter per second. It is slower than what I had. I was going 15.2. I hit a patch of friction. Now I'm going 14.1. It's slower. It's not a ton slower. And probably it shouldn't be because that coefficient of friction was not particularly big. So I did slow down by a little bit. Now I'm going to go from D to E. So from D to E, my energy at D is equal to my energy at E because I have no non-conservative work. So that's what I'm going to do. My energy at D was mg, height at D, plus half m, speed at D squared. My energy at E is just potential energy. I'm looking for I'm looking for height at E. And it's just potential energy because if I had any kinetic energy left, I would be, well, not stopped yet. Mass cancels because it's everywhere. And I am searching for HE, solving for HE. So let me do that. HE will be G times height at D plus half speed at D squared, all divided by G. So I can plug in 10 meters per second squared. I've got a negative 10 meters. Half of 14.1 meters per second squared. And I'm dividing that whole thing by 10 meters per second squared. And I get that my final height at E works out to be, let's see, I've got negative 100. 14.1 squared times a half is just about 100. Is 99.4. So negative 100 plus 99.4 is negative 0.6 over 10 is negative 0.06 meters for my height at E. This came out to be a negative number, and anytime I've got something like a height that comes out to be negative, I want to take a second and pause and make sure that I'm actually doing this right, that I didn't make some kind of a mistake. It's totally fine for negative numbers, but they do make me want to pause and check. Negative 0.06 meters means from this starting height, because this is where I called my h equals 0, from this starting height, I am going to end up 6 centimeters down. So from the ground underneath, if I'm asking how high up the box, or up the hill the box is going to reach, from here, this whole distance is 10 meters. This whole distance is 6 centimeters. So the distance from the bottom, like the distance that I've made it up the hill, is going to be 9.94 meters. And that does make sense to me. Now I told you that we can do this problem 2 different ways. So that was the first way. Here's the second way. I can look at this, and instead of worrying about all the in-between steps, I can say my energy at A plus all my non-conservative work is equal to my energy at E. My energy at A, that's 0. That's nice. My non-conservative work, I've got energy that I've added, push times distance AB. I've got energy that I've subtracted, mu k mg, the distance from C to D, equals my energy at E, mg, he. For me, if I am doing this problem and I don't have to find my speeds in between or anything like that, I'm just going to do this. I'm going to say, let's skip over points B through D and just compare A and E. I've got a couple different spots where there's work being done, non-conservative work being done. I've got one spot where I'm adding, one spot where I'm subtracting, and then a bunch of zeros. I can just compare those directly and I don't have to do all the in-betweens. But a lot of times in problems like this, you'll be asked to find the speed at these different locations anyway, so then going through the process isn't the worst thing. That's it. That's a very robust example of how to do a problem with non-conservative work.